Good evening, children.
Good evening, sir.
So, kinematics of circular motion continues. Can you just remind me the summary of what we did until now? In short, we talked about the acceleration in a circular motion. Isn't it so? Children, when a particle is moving in a circular path, in general, we have told the acceleration can be thought of as having two parts, a tangential and a normal. The A total being somewhere in the middle of the two. This is the instantaneous acceleration. That is acceleration at this instant. Right? And what did you say? This A can be written as what? Hello. A tangential square plus A normal square, and tan alpha equals A normal by A tangential. I'm giving the summary of what we did until now. And we could also write in terms of vectors A equals what? In terms of unit vectors defined in this direction, children. That is, we defined one unit vector called ET cap in this direction, ER cap in this direction. So in terms of the vector notation, we can write it as what? Minus V square by R ER cap plus D mod V by dt E tangential cap. So this itself says that this V square by R is towards center, and this is only the rate of change of speed. Rate of change of speed. And this is the normal acceleration or the centripetal acceleration, which is the reason for changing the direction. Reason for changing the direction of the part motion. All right. And if A tangential is 0, it implies mod V is constant. And this type of motion is referred to as what? Uniform circular motion. But if AT has non-zero value, it is non-uniform circular motion. Isn't it so? Hello. Children. So why am I revising? Look, we went for details, we derived the relations, but ultimately the summary of it is what you require to do problems. The formulas as people use it are actually the summary of a physical drama happening there. So the summary, if you put in mathematical form, but don't forget the meaning behind it, then you are in a position to apply it somewhere. Okay. Now, what else? And I've shown you the examples. The question is also there, like how that can be used in simple questions. And see, we can also express the same A in a slightly different way. Look, I can also express this A. See, what is important is A. This A tangential, A normal, or for our convenience, we are resolving that A into parts. But otherwise, I can also express the same A in a Cartesian coordinate system like this. The three-dimensional XYZ coordinate system. Hello. Instead of choosing the origin there and moving the coordinate system along with the particle, here what I do is I will express the same A in this coordinate system. This is X, this is Y, this is Z, and our A here, this is A we told for the particle. Now you can think this A to have three components: AX, hello, AY, and AZ. So one can write it as what? A bar equals AX I cap plus AY J cap plus AZ K cap. This is purely analytical way of discussion for A. This A will be simply with respect to this origin we have taken. I'll use a different color. This is the radius vector, children. Joining the particle to the origin. This A will be d square r bar by dt square. If you remember acceleration, the second derivative of position, our job is done. If in a single dimension, if the particle is moving in this x direction, if this is position x from the origin O, Vx equals dx by dt, we write. If I wanted acceleration in this direction, what do I do? Ax equals d of Vx by dt. That is d of dx by dt by dt. This is what you mean by d2x by dt2, or d square x by dt square. This only tells you that this position coordinate differentiated once gives velocity, differentiated twice gives acceleration. Therefore, this r bar also you can write. So this is the same acceleration in a different coordinate system is represented in terms of what? Ax, Ay, Az. Do you follow? Of course, we can connect these two things also. Even that I don't mind doing, but a little later time we'll do that. Here, this none of the components need to be towards center. Do you follow? Not only for this circle, even if it is going in a very zigzag path, still I can discuss. I can express A in terms of its components along the x, y, z directions. Okay. What you need to understand is the same acceleration can be given in two ways. But remember, what is real is A. A doesn't change even if you change the coordinate system. Try to understand that A is A. A is a unique vector. It has a physical meaning for the particle. What is the physical meaning for the particle? This A characterizes the change in velocity per unit time. But change in velocity could be in terms of direction. It could be in terms of magnitude. So the first way defining gives a little what you call easy understanding when you apply it for problems, and you'll see that in dynamics. Okay. Are you there in the meeting, children? Hello? Hello?
Yes, sir.
It is getting stuck. Let me see. Okay. Hope you understood the whole thing. We are still in the formulation of the ideas, like when a particle is going, that means already going there. You are told that it's going in a circular path. You're not going to decide whether it's going in a circular path or not. That kind of a problem will be slightly mathematical. They'll give you the position xy and then they'll ask you the path. They'll give you xy in terms of time and then they'll ask you the kind of path. So in that you eliminate the relation between x and y gives path. That's another what you call another side of the same coin called kinematics. What do we mean by this? In kinematics, you are given position, you can find velocity and acceleration. You are given acceleration, you can find velocity and position. If you're given position in terms of time and eliminate time from that, connect the position coordinates, you get path of the particle, which you've seen in our projectile motion. Do you remember? When a particle is projected like a projectile under gravity, like when the motion is taking place in 2 dimensions, we removed t out of that xy coordinates and we got a parabolic equation, right? So x to v, v to a by differentiation, a to v, v to r, that is position from integration. So that whole kinematics is about differentiation and integration, children. Right, now shall I continue? Have you written down the things there? Hello, are you there in the meeting, children? Vishnu?
Yes, sir.
Now we'll go for certain other things. We talked only about acceleration until now. That's the most important thing anyway. And last time I've shown you a few problems as well. Now let me talk about certain other things. See, when a particle is moving in a circular path, when a particle is moving in a circular path, there are 2 things happening. What are those 2 things? Some linear distance is being covered and some angular displacement is being covered. So when a particle is moving in a circular path, one, some linear distance is being covered, isn't it? I hope you followed the distance. Some linear distance is covered or being covered, doesn't matter. 2, some angle is being described. Hope people follow the meaning of it. Like when you are talking of a particle going in a circular path like this, supposing if I take my origin here, as x and say this is y, for example. Now the particle started at t equals 0 here, for example. In delta t time, the particle is there. This is my particle. So in a delta t time, it has described a linear distance of delta s and an angular displacement, people call, I don't know why, but some angle is being described, that is delta theta. So this is what I mean. That's what you mean by saying that linear distance is covered, angle is being described. So when you're talking of a circular path, when you're talking of a circular motion, that can be described, that can be understood in terms of both linear quantities and angular quantities. Therefore, we can analyze the circular motion both in terms of what? linear quantities, and angular quantities. First, I'll make it simple by taking my origin at the center of the circle. But remember, to make it more general, I should be able to, I should take the origin anywhere and describe my whatever quantities I was mentioning, which I'll be doing slightly later. Let us not lose the meaning of the thing in the mathematics. So in the beginning, I'll make it mathematically easy, but physically very meaningful to us. Now, I'll draw my, no need of drawing because already there. Like, see, first quantity I define is average speed of this particle going in a circular path will be, I can say V average, but remember this is speed, not velocity. This is speed, not velocity. That should be simply this delta S by delta T. It's path length by time, not displacement by time. Hope you understood. It's not this one we wanted, not this one. That will give you average velocity, that will be called delta R. We don't want that. When you're it's not that we don't want. What I mean to say is if you're taking the paths here, you'll get speed like that. V average equals what? Delta S by delta T. Do you follow? But immediately comes the instantaneous speed. Instantaneous speed. That is V instantaneous, or simply V. If you just write V, it is instantaneous. If I put some brackets like this, or if I put some bar like that, that is average. That is a what you call a notation people follow to represent average. So instantaneous speed V will be limiting value of that, limit of delta S by delta T as delta T tends to 0, and this will be given a name ds by dt, which we have done already. But we are revisiting the whole idea once again in terms of the circular motion. When a particle moves in a straight line path, there are no angular quantities, I mean, to begin with. Not that you cannot bring angle into this, but for an intuitive understanding here, when I say intuitive understanding, what? If I'm not making it mathematical, analytical, there's no need to talk about theta here. So it's a straightforward thing, like a particle goes in a straight line, no angle described anywhere, you can say. All right. But the moment the same path bends into a circle, at the center of the circle, even angle is being described. So when you are looking at the motion of a fan, you'll understand that. Every point in the fan, here I'm talking of a kinematics of particle. I'm not talking of the fan as a whole. So when a fan is turning like that, a point on the fan is going in a circular path. In fact, the circular paths of many particles in the fan, which are frozen into the shape of a fan, is the total motion of the fan, which people call as a rotation. I don't know whether you understood my words. Hello, children. If you make a mark there at one point on the blade of the fan, you'll see a circle, don't you?
Yes, sir.
Huh?
Yes, sir.
So like that, if you think of many points on the fan, the combination of the circular motion of all the particles together for the fan will be called rotational motion of the fan. So that's why, remember, what all is talked here has a direct application here, and this is the basis for the future. And if what certain words are mentioned here, certain definitions are given here, remember, there's going to be an application or a numerical problem, or there's going to be a practical application of that in future. So there's a path covered, that path by time gives you average speed. But if the delta t is becoming very, very small at a given time t, you'll discuss that. You will define that instantaneous speed. So the first quantity, the second quantity as a linear quantities when you're talking. And then average tangential acceleration, which we derived the other day. Average tangential acceleration, that is, you define it between two instances, t1, t2. A tangential average, if you remember, was what? D that mod v, which may be this one, dv by dt, no vector sign. This is not dv bar by dt. People should be very clear about it. This is only rate of change of, sorry, I should have written it as not delta dv, isn't it? I should have written as delta v. Average will be always that delta v by delta t. Instantaneous tangential acceleration is simply the limiting value of this, which is written simply as at equals dv by dt. So the motion can be understood in terms of s described. S here is not the displacement. S is the path length, arc length, as a particle moves from one place to another place. So between two instances, t1 and t2, you define average speed and make it instantaneous speed. Similarly, between two different speeds, you define tangential acceleration and make it instantaneous by bringing the time interval to 0. So this is all about the linear quantities. But you can as well define the angular quantities, children. You can as well define the angular quantities. Hello, you're not speaking, children. Are you there? Hope you're all
Yes, sir.
not sleeping there. Now, angular quantities, if I define, angular quantities. You have the, once again, I'll take my circle. Yes, the same center I can take. This is my x, this is my y. All right. Now we have the particle here at t equals 0. The particle is here at t equals delta t. So I told you this delta theta is described. Now this happening in the same time delta t, isn't it so? We had, of course, this delta s described. This path by this time gave you average speed. This angle by this time gives you average angular speed. Is it okay? So the angular quantities, first thing is what? Average angular speed. Will be defined as omega average with this bracket, this kind of brackets, is delta theta by delta t. Angle described by time taking, to put it in more simpler English words. And what comes after that? Could you tell me? Children.
Yes.
Instantaneous, right?
Instantaneous.
Actually, I was using this because this allows me more flexibility with my writing. But this mirroring is having some issues. Right. Second is what? Instantaneous angular speed. is equal to limiting value of this, right? I need not have to write it again and again. Can I write it as omega equals d theta by dt straight away? Come on, once you understood delta y by delta x is average and dy by dx is instantaneous, now you've got so many things like that in physics. Huh? Of course, the units are here, radians per second. For that are this. Previously, meters per second, all that you already know. And you know how to define a radian from mathematics. In fact, that also I defined in the beginning when I started doing some maths for physics. Right. Then comes, after this, omega changes its time. So you get average angular acceleration. Average angular acceleration. Straight away I can write as what? Alpha average. Or if you don't want to write those brackets, you can write alpha AV, you can put if you want. Is equal to change in angular speed by time, omega 2 minus omega 1 by T2 minus T1, which is written as delta omega by delta T. All right. And immediately follows instantaneous angular acceleration is d omega by dt. The units will be radians per seconds per second, or radians per second square also you can tell if you want. It should be radians per second per second. So that way you will not forget that it is velocity change. Radians per second is angle change, rate of change of angle, that is. Okay. So any questions until here, children? Or you say, why are you talking like this? Why can't you just go starting some multiple choice A, B, C, D? Right. How do you visualize angular acceleration, children? Or how do you visualize constant angular speed? How do you visualize constant angular speed? In your room, there must be a fan. Look at it. That is constant angular speed. That means if we can somehow count in every 1 second, the angle described will be same for that. But now go and put it off. Really do it for a while. That is angular deceleration. Once it's stopped, switch it on again until it becomes uniform. It speeds up. The angle described will be more and more in the later seconds. That is called angular acceleration. But once it settles down like that, once again, physics in that, try to understand why is it settling later, why is it first turning slower or turning faster. Once again, is physics only, complete physics inside. You need to know some electricity and motor business also. Electric motor, if you understand, you'll know that, even that. And if anybody says, come on, this physics we don't use later. Yes, we may not use it later exactly the way it is meant, because the classic, the old industry is already been saturated. But remember, the same principles will be applied everywhere. So I've been telling you previously, linear acceleration, how do you visualize means I told you. First 1 second, x distance. Next 1 second, 3x distance. Like that, as you go forward, if it is accelerating, the distance will be going on increasing if it is a straight line motion, or it will be going on decreasing if it is a straight line motion, but if it is linear deceleration. But here we're talking of angular acceleration, angular velocity. So when a particle is moving like that, I can talk about angular quantities and linear quantities. So there's one more thing I would like to add. Logically speaking, look at this. there are three quantities, delta S, delta T, and delta S, delta theta, delta T. Am I correct?
Yes,
Hello?
sir.
This is delta S,
Delta, yes.
delta theta, delta T. So what we have done is we found out the rate of change of delta theta on time and delta theta on delta S on time, but we did not check it rate of change of delta theta and delta S. Does it have a meaning physically? It has. Can somebody tell me what is it? Make a guess. That's called the radius of curvature. Of course, in the case of circular motion, the average radius of curvature and radius of curvature at every point is same. But in other things, they are different. So I can also talk about, we can also talk about, tell me what should I write? Talk about the rate of change of, tell me, delta theta on delta S or delta S and delta theta, doesn't matter. I should write, say, I'll write delta S on delta theta. So here comes R average, that is average radius of curvature. R average is delta S by delta theta. Instantaneous radius of curvature. Instantaneous radius of curvature will be R equals limiting value of this, that is limit of delta S by delta T as delta T tends to 0, which will be termed as ds by, sorry, here theta, ds by d theta. This R instantaneous. In fact, people know this, ds equals R d theta, you write. If you integrate from 0 to S, 0 to theta, you will get S equals R theta. This is the relation between the linear quantity and angular quantity. Hello. But in theta should be in radians. Hope people followed it. How? If it is starting here and went there, how many radians it described? 5 by 2. So this arc length will be how much, children? Hello, this radius is, for example, 1 meter. So this arc length will be how much? S equals R 1 meter into theta in radians. So pi by 2 meters, isn't it? So that's what it means to say S equals R theta. We said when a particle moves in a circular path, there are linear quantities and angular quantities. So once you define them, you should be able to connect them also, right? And for a circular path, this average, R average and R instantaneous are one and same. For a circular path, R average is equal to R instantaneous. But for some zigzag path like that, it will be different. You need to take average radius of curvature between 2 points to be different from the instantaneous radius of curvature here. This instantaneous radius of curvature. But from this point to this point, something else will come. So for circular path, everywhere R is same. And this radius of curvature business is very, very important for future. And there will be a thing called curvature. You define curvature as the reciprocal of the radius of curvature, children. Curvature is equal to 1 by R. The reciprocal of the radius of curvature is called curvature. Yeah, that way of discussing will be somewhat useful in many times. For a flat surface, R is at infinity. A flat surface, if I take, R of this will be at infinity. I don't know whether you understand the meaning of it. It is to say that the radius of curvature equals 0. Because 1 by infinity. Do you follow? To say that it's flat, mathematically we say its radius of curvature is infinity. Therefore, its curvature is 0. Curvature is 0 means flat. And you know, if you take a pear-shaped object, somewhat like that, here the radius of curvature is lowest. So curvature is the highest. Here the radius of curvature is flatter. It is more. So radius of curvature means here itself you should draw one circle like that to understand the radius of curvature there. But at the pointed edges, R will be almost, tell me, 0. So curvature is very large. So pointed edges will have more curvature and the flat edges have less curvature. Do you follow my point? Huh? Hello. Pointed surfaces have more curvature, which is intuitively very easy to understand. The curviness is more. So curvature and radius of curvature, both are different. Curvature is 1 by R. Hello.
Yes.
If R is 0 at the pointed edge, curvature is infinite. So that's going to be very important for us. Any questions, children, before I continued? No, if you're very, very silent, that is dangerous. I told you many times. Yeah, say for example, you cut your nails in such a way that somewhere here you have the pointed edge in the middle. Side by the curvature is less, but at the pointed edge the curvature is high. All right.
Yes.
So remember, I started just looking at simple 3 quantities: linear path, angular displacement, time taken for that. Out of that, we pulled out 3 quantities. One is angular velocity. Of course, in that once again, average and instantaneous. Other is linear velocity, linear speed. Hello, or the magnitude of linear velocity, doesn't matter. So linear speed. In that once again, average and instantaneous. Then curvature, radius of curvature, average, radius of curvature, instantaneous. Why are we discussing all these quantities? The quantities are there, and then by defining them, there means what I mean to say is there the what you call the mathematical nature of physics is that physics likes to be expressed in mathematical terms. So what I mean to say is that the thing is already there in the nature, that curvature, speed, angular speed. Only we are grabbing it and putting it that in a on a paper. So three physical quantities are what you call extracted from the nature there. Right now, later we'll come back to more discussion. Look, but I'll tell you something very interesting. After that, I'll go for what I wanted just now. I can divide the kinematics in terms of A and A tangential and A normal, children. Classification of motion. Just a minute. Classification of a particle's motion in terms of the values of A normal and A tangential, children. Just a minute. Classification of motion of a particle in terms of A tangential and A normal. I'll give you the clue. You try to understand it. I mean, you try to name and you try to identify it. A tangential is 0. Sorry, A tangential is 0. A normal is 0. The first kind. Could you tell me what kind of a motion is it? If you're able to answer this, I can say that you've been following my lesson. Hello.
Yes, a particle is moving in a uniform velocity in a straight line.
Uniform velocity in a straight line. Not a bad thing. Like, look, it's going like that in a straight line. Right? The speed doesn't change because AT is 0. Speed V is constant. And direction is not changing. Isn't it? That means it is straight line. If an A normal is there only, there is a direction change. Direction is not changing. Therefore, it is straight line motion with a constant speed. Right? Hello?
Yes.
So it is, I need not have to write it again because I'm showing the straight line there. The second kind will be AT is not 0, AT is constant and A normal is 0. Tell me. Somebody else now take the lead. What kind of a motion is this? It is once again a straight line motion, but constant acceleration. Constant acceleration. I don't know, you're not saying much. Now 3, AT is variable. A normal is 0. Once again, a straight line motion, but change variable acceleration. Straight line motion, but variable acceleration. The acceleration itself varies. And here we use differentiation integration very liberally. So straight line motion, which can have three kinds. One is it can go in a straight line, the speed remaining constant. 10 meters per second means 10 meters per second all the time, at every instant. That means instantaneous speed is constant. That's what you mean by the first kind of motion. In the second kind of the motion, the speed goes on changing but uniformly. 2, 4, 6, 8, 10, 12, like that. That means the distance covered by a nice ratio, like probably 1:3, 5:7, like that. AT is variable. The acceleration itself changes. So there is a third kind of motion. All these three motions we dealt with in great details, actually speaking. Now three more. Can you now make a guess on your own? Fourth one. AT is 0. A normal is constant in magnitude.
Yes, sir. Uniform circular motion.
Yes, uniform circular motion. Isn't it? What
Yes,
does
sir.
it mean, children? Here, once again, I'm telling this so many times with the hope that, oh no, before that, a fear that you're not trying to understand and you're not writing, when I don't know whether you're writing or not. But with the hope that listening to this too many times at least will that will settle in your mind without your effort also. So this center we have here, the acceleration is towards center all the time, and the velocity vector is constant in length. Hello. This is quite an interesting kind of motion. I'll come back to this again and again. This is AN is constant magnitude. I'm saying why? Because it is going on changing direction. No? Now it is upwards, then it is this way, then it is downwards, then it is this way. Of course, if you are saying that it is constant because it is towards center, that's one kind of a statement. But for the vector sake, if you take from the outside, that A is changing all the time, isn't it? If I look in the XYZ coordinate system, that A is changing direction every time. So this is uniform circular motion. And fifth case is what? AT is constant. AN is also constant in magnitude. This motion is what we call as a non-uniform circular motion, but a special type where AT is constant. AT is not variable. So I can't show it anyway. Like what I show it means, like I can only show this way. You draw the circle. Now the way I can show it is what I already have shown you. V1, V2, like V3, but this should be a constant variation I should have. This is that. But the sixth case can be what? AT is variable. A normal is also variable. So whatever application in kinematics you do, it's just one of these six cases. Of course, here I took only straight line and circular motion. I did not take into consideration that parabolic motion or some general curved motion. Even for that also similar ideas will come, but that is slightly different. We can discuss it if you're comfortable with these things. So within our syllabus scheme, these are the only 6 kinds of motions we deal with. Tell me, children.
Sir, in a non-uniform circular motion, AN is constant or variable?
Tell me again.
In a non-uniform circular motion,
Sorry, that's nice. Sorry, that's not correct. Good. AN is also variable. Why, you know? Hello. That's right. If
yes, sir,
AT
V
is there,
square by
speed
R
V changes and V square by R keeps
changing.
Huh?
Yes, sir.
Good. Thank you. Yeah, if you're sleeping, you won't even catch the mistake we do. Hello. Others. Hello, children. Are you listening? Many are not there in the class only. So this is a nice way of yeah.
Sir, when AT is constant and AN is also constant, what kind of motion it is? Both AT and AN are constant.
Tell me again.
Both tangential acceleration and normal acceleration are constant.
They cannot be, right? Just now you pointed out, no?
Yes, sir.
Then now that was a mistake by writing constant there. AT is there means V is changing.
Yes, sir. V is changing.
So V is changing means V square by R keeps changing, right?
Yes, sir.
Hello, children. This went off. Is the screen being
Visible,
shown to you?
Yes, sir. Yes, sir. Visible.
It is visible means it is not
The
hidden
presentation is
somewhere.
visible.
Do you see it on my tab somewhere here?
We can only see the presentation, sir.
Why it is gone like that? For me, it is missing. I just wanted experimenting with this because I told you already, the iPad writing will be nice. When the circles, these things I can bring in. But suddenly, this fellow went away somewhere. I don't see it on the taskbar anywhere. Is this that one? No. You can see my iPad. Hello.
Sir, only the presentation. Yes, sir.
This we can see, but for me, suddenly it went away somewhere. Oh, it's not there on this. Okay. Anyway, it's time. Come prepared with this properly. I'll be continuing the lesson from tomorrow. I'm not finding it anywhere. Maybe if I close and I may come back, but let me try a little, just a minute. I think they gave this option very recently, actually, to mirror the iPad on Zoom. So I think it is still not very good. No, it's not. I cannot, of course, I can write. If you're able to see, you tell me. That's not important that I should see there on that. Okay, now we have shown that SE equals R theta. Can you see this now? SE equals R theta is visible to you?
No, sir.
No.
No.
Okay, then I think I'll close it for today. Tomorrow we'll meet again. Hello, children.
Yes. Thank you, sir.
Right.
Thank you, sir.